All right. Welcome to our stats lecture. This is lecture 9. We're going to talk more about the normal distribution, and we're going to talk about one of the key ideas in using statistics in all of our different ways, the central limit theorem. So first, let's just do a quick review of the normal distribution. Basically, any continuous random variable where observations near the center of the range are the most common, and the probability of observing values go down. Let me say it this way, it goes down the farther from the center you are. And this version of farther is actual distance. All right, so we have a continuous random variable where the observations near the center are the most common, and observations farther away get progressively less common. It might not be exactly a normal distribution, but it's approximately normal, i.e. bell curve. Well, let's look at that. Okay, so if I'm in the center of the range, I have a high probability, and the farther away I am, the lower the probability. That's going to trace out a bell curve. So even if we don't put any numbers on it at all, that shape comes from observations near the center are the most common, and they get progressively less common the farther away you are. And it's going to give you something that looks at least kind of like a bell curve. That very center is the expected value. So we'll call this a distribution of a random variable x. And every distribution has a standard deviation. It just so happens that with normal distributions, 2 standard deviations covers just about 95% of the data, with only 5% in the tails. So 2.5% in each tail, 0.0205, 0.0205. It's not exactly, but this is statistics. We don't have to be exact. It's very close to 5%. And that's the probability that humans have decided is statistically surprising. So often with normal distributions, we get to use the 2 standard deviation rule. That's one of the reasons normal distributions are so nice, is because the calculation becomes very easy, especially in the old days when people didn't have computers to do calculations for them. So let's do an example. The mass of an egg is approximately normally distributed with a center and expected value at 50 grams and a standard deviation of 5 grams. So we can draw our distribution here. I like to draw the bell curve first because if I draw it badly, I can just adjust where my mean and standard deviation are. On that one, I did pretty well. There's 50 grams. And then I just kind of eyeball like what would get me to here, and then I go halfway. And so that distance there is 5. So that means this is 55, and that's 60. And that's 45, and that's 40. And this is my distribution of x. I'm not putting a vertical scale on there because that vertical scale is kind of less important. When you look at a probability distribution and you want to figure out probabilities, you don't look at the vertical scale. What do you look at? Probabilities in a continuous distribution are found through, anybody remember? Recording. How do you find a probability of a continuous variable from a graph? You look at an area, right? That's why we say this area is 0.025. That means the probability of being out in this far upper tail is only 0.025. It's 2.5%. Yeah. That's the whole reason for having the pictures, is it can make the probabilities a little bit easier if you can see it in a picture. The app that we use, we'll actually come back and use that for one of these questions. The app shows you areas, which are the probabilities. Okay, so would you be surprised to have an egg with the mass equal to 58 grams? There's our picture. Let's get it focused. Focus. Okay. Would you be surprised to have an egg with a mass equal to 58 grams? Talk about it with your neighbor and decide. What did you think, Gabby? Yeah, right. We use our 2 standard deviation shorthand for normal distributions. 58 is here, it's not past the 60. Now this brings up an interesting question. What do we mean by more extreme than 58? Most of the time in a normal distribution, more extreme means above or below the same distance. All right, so we think about it, either you can think about it symmetrically or think about it two-tailed. So let's grab the app and just confirm our suspicion or the intuition that, well, it's not more than 2 standard deviations, so the probability is not that small. But remember, ultimately, we always make decisions about probabilities when we're talking about statistics. The mean was 50, the standard deviation was 5. And there's that distribution, drawn a little bit better than mine. And we think about it in two tails or on both sides. So we're going to look outside of a region. 58 is to the right. And then we need to go the same amount down to the left. which would be 42, right? 58 is 8 more than 50. 42 is 8 less than 50. There it is. Yeah, and there's still an 11% chance of seeing that egg. So statistically speaking, not surprising. The omelet, maybe not that tasty. Oh, wait, it's bigger. Yeah, no, nice hearty omelet, but not that surprising. I'll add these notes later. Well, no, I better add them now. So no, because the probability of observing an egg with mass 58 grams or more extreme, two-sided, is 0.11, which is not less than our usual cutoff, 0.05. All right. What about an egg with mass of 37 grams? Would that be statistically surprising? Here, let's do this. All right, an egg with a mass of 37 grams. What do you think, Bella? Well, then why is that? Yeah, so because we're using normal distributions, we get to use this 2 standard deviation shorthand, and 37 is not within 2 standard deviations. If we wanted to check our two-sided probability, that's 13 below, so we want 13 above. That's only a 1% chance. Only 1% of chicken eggs, on average, are 37 grams or less, or 63 grams or more. And that's, I mean, that's the definition of surprising, is you only see it 1 out of every 100 times, so you'd be surprised. Yeah. So I would say here, I would say yes, because, let me put that up there. The probability of an egg with mass, let's just keep it short, more extreme than 37 grams is 0.01 or 1%, which is smaller than the cutoff. The 2 big advantages of a normal distribution. First, it's really easy to use mathematically. And second, there are so many things in this world that are normally distributed. Alina, would you close that door? Thank you. The mass of chicken eggs is actually pretty close to normally distributed. Height is normally distributed. Fluctuations in high temperatures tend to be normally distributed. There are a lot of natural or physical phenomena that are more common near the center and get progressively less common the farther away you go. Unfortunately, there are also a lot of natural phenomena that are not normally distributed. And if they're not normally distributed, we don't get to use these tools. We don't get to say, oh, it's more than 2 standard deviations, I'm done. But that's where the central limit theorem comes in. Let's start with a picture. Suppose the weight of cats is not normally distributed. That's actually a bad assumption. It probably is normally distributed, but I'm going to use cats for the example. We can still model that distribution with the probability, or model the weights with the probability distribution. And let's say it looks more like, well, like this. Right, where we have a low end, maybe that's 5 pounds. And we have a high end, maybe that's 20 pounds. And there is a vertical scale, but the vertical scale is less important than the total area. What's the total area of the shape? 1, because the total area of a probability distribution is always 1. Yep. Can I use my normal distribution tools when asking about surprising cats? I cannot, because it's not a normal distribution, right? If the wrench doesn't fit, you can't use a wrench. However, it does still have an expected value. It looks like it's right about here. Just kind of guessing. And this is not a case where observations close to the expected value are most common, and it gets less common the farther away you get. In fact, if this were true, you would be more expected to see heavy cats or light cats than cats that are close to the middle. So if you're trying to understand, excuse me, the distribution of cats and their weights, the tools with this probability distribution aren't very useful. But what's one simple thing we can do in statistics to get a better understanding of the system? Exactly. So let's collect more data. Instead of just picking one cat, let's pick a sample. How about 30 cats? All right, let's pick a random sample of 30 cats. I pick 30 because that's kind of our cutoff for enough data to do pretty good statistics. And let's find the sample mean of the weight. So the X bar, not the weight of an individual cat, but the sample mean. Where do you think that sample mean is going to be on this range? In the middle. And why do you say the middle? Because it's always the middle. Because the whole point of an expected value is that's what you expect to get when you do an average. So yeah, I mean, if we plotted that, it probably wouldn't be exactly at the expected value, but it might be close. Right? This sample had a few more cats that were less than cats that were more. Now let's imagine doing this again and again and again. In reality, you would only do this one time, because I'm not going to go out and grab 30 random cats and then come back the next day and do it again and again and again. But if we did it again, we'd get another sample average. And where do you think that sample average would be? Close to the middle, maybe over here this time. And if you keep doing it, would you agree that most of the time you'd expect to get something close to the center? But every once in a while, you're going to grab a sample of cats where you get a whole bunch of chunkers, or a sample of cats that are all just super little and skinny. But nevertheless, most of your sample averages will be close to the middle, and those sample averages become progressively less likely the farther away from the middle you get. What kind of distribution are my sample averages? This is a normal distribution. Not of the variable x, but the variable x bar, the averages of samples. Can I use my normal distribution tools on this lower distribution? Yes, because it's a normal distribution. So now I get to do things like how far away is 2 standard deviations? And is it surprising because it's more than 2 standard deviations or not? So simply by doing good statistics, by collecting a sample instead of a single observation, I unlock the ability to use my mathematical statistical tools. And that's exactly what the central limit theorem is. It's the theorem that says it doesn't matter what your initial distribution looks like. If instead you collect data, that data's average will be normally distributed. And now you can use your normal distribution tools on your data instead of on a single observation. So I'm going to write down the central limit theorem a little more explicitly. But still kind of putting it in my own words. I wrote it backwards. All right, let's try it again. Focus. Thank you. The central limit theorem. Central, I hope, is kind of obvious. It says that your averages are close to the center of your data. Limit is a mathematical idea that basically means do this again and again and again in an infinite number of times. And the more you do it, the better it gets. And a theorem is something that was investigated mathematically and proven to be true. Let x be any random variable. I suppose it has to be continuous, but I'm just going to say any random variable, even if it is not normally distributed. Collect a sample that is large enough, usually at least 30. So I'm going to do n greater than or equal to 30. Then the distribution of the sample mean will be normally distributed. That's the first conclusion of the central limit theorem. Is doesn't matter what your variable looks like, the sample means will form a bell curve. But there's more. The expected value of the variable is e of x. The expected value of the sample means, expectation of x bar, e of x bar, is also e of x. I'm going to show you that on the picture that I drew once you get this written down. Every probability distribution has an expected value. And if you look at the distribution of the sample means, those will be centered at that same expected value, which is exactly what Lily said, because they're always in the middle. Right? If they're always in the middle, that's where it's going to be centered. And there's one other useful piece. This is maybe the most confusing useful piece in statistics. There's plenty of really confusing things in statistics, but most of them aren't useful. This one's very useful, but it's also very confusing. The standard deviation of the variable is SDdev of x, often written as the letter S. The standard deviation of the sample means, because those are going to spread out, right? Not every sample mean will be the exact same. You're going to have some spread, but it's smaller. It's smaller because we're collecting more data. And if you want to do better statistics, you collect more data. And when you collect more data, your estimates are more accurate. Notice how this CATS distribution is spread between 5 and 20, but most of the means are close to the center. It's not spread out as much. And I just drew this by hand. I'm going to show you using R how that works. And we have a calculation for it. The standard deviation of X bar is the standard deviation of the variable, but we divide it by the square root of the sample size. Collect a big enough sample, the means will be normally distributed. They'll be centered at the same place as your random variable, but they'll be spread out a lot less. And this is basically the number, how they're spread out. So I'll just do one quick example, and then I'll show you in R what that simulation looks like. So suppose the expected weight of cats was, going off here, I'd say that's 11 pounds. Whoa, that's yeah, 11 pounds. And the standard deviation for the cats is, looks like about 5 pounds. Just eyeballing my picture that I drew. Okay. A sample of size 30 will have a sample mean where the expected value of the sample mean, this one you all can just tell me, is what? £11, because it's the exact same. But the standard deviation of the sample mean, it's not 5 pounds. It's 5 pounds divided by the square root of 30. All right, it's 5 divided by the square root of the sample size, which is 0.91 pounds. And it spreads out a lot less because most of your sample means are going to be really close to 11. The actual computation is not the most challenging. Once you've written it down, you can do it every time. What's challenging is the question that I'm going to ask you next, what I have found to be challenging. And you get to answer this question in your lab as well. Okay, assuming you have those details in your notes, because you can't see them on here right now. In statistics, we always like to, at least I always like to come back to the would you be surprised question. Would you be surprised by a cat that weighed 15 pounds. Is that a surprising weight for a single cat? Focus, please. Sorry, I'm going to try to get it focused. Talk with your neighbor, decide if that's going to be, if that would be a surprising observation to see a single cat that weighed 15 pounds. Go ahead.
Thinking that it wasn't surprising because it was within standard deviation.
Now we got to be a little careful here because cat weights are not normally distributed. So we can't jump straight. Come on. We can't jump straight to the 2 standard deviation rule. But nevertheless, here's 11 and here's 15. And that's really not that far away, right? It's not extreme. So we have to be a little careful with the 2 standard deviation idea, but something that close, especially if it's within 1 standard deviation, even if it's not normally distributed, that's not surprising, right? So not surprising because, again, the probability of a cat weighing 15 or more extreme is pretty large. I can't tell you the exact number, but I can use a visual analysis to say it's pretty large. There's a lot of that curve more extreme than 15 and or like more than 15 or less than 7. Right. Okay. Would you be surprised if the average weight of the 30 cats you treated, here you're a vet, today was 15 pounds? Talk about that question with your neighbor. Again. So this is surprising. Because I'm working with a sample of 30. So the average of that sample should be very close to 11 pounds. I need to use the distribution of the sample means X bar. I'm not going to use this distribution anymore. That was just for 1 cat. I'm going to use the normal distribution for my sample of size 30. And that normal distribution looks like this. Again, I don't worry so much when I'm drawing it. I just make sure my scale fits. This is the distribution of my sample means, my X bar. So what should the center be? We have it on our previous page of notes. What's the expectation of X bar? 11 pounds, because that one is the same as for any given cat. But the step size is now 0.91 pounds. So 1 standard deviation is what, 11.9, and 2 standard deviations is 12.8. And I'm way up here at 15, which is basically, I would be super surprised. Now I'm a vet. Do I just throw my hands up and say, what a weird day? No, I say, okay, that's surprising. Let me do a little more looking. Right? The reason we look for surprising results is it gives us a clue, aha, there's more to investigate. Because statistics just tells us it's not what we expect. But the science and the curiosity is where we say, because it's not what I expected, it's worth looking into more. Maybe a cat carnival came to town and they were all Maine Coons, right, which is a large breed of cat. Or maybe, there's been a lot of marketing and people are buying a certain type of food that's leaving it overweight. We don't know why it's above what we expected, but since it is way above what we expect, it's worth doing more research. Okay, I think I'm going to leave it there. I'm not going to do the R example. Maybe I'll come back and I'll do it another time. But you all in the lab, lab 2, when you're working with your continuous distribution, whether that's precipitation or I think probably salary and either one of the blood pressures or glucose, you will be looking at the distribution of your data and then the distribution of the means of samples. So for the rest of today, you can work on that. I'm going to stop recording.